Can we pose the same problem without making this assumption? That is the idea. And I told you already, my mother told me, don't ask a question unless you know the answer. Okay, so here's what I did. First of all, I asked myself, what is going on in this particular drawing? The momentum transfer is the answer. Even if you don't know what that means, that is the answer. Momentum transfer, movement. The mover is transferring that to the wall. The wall receives it as the feeling, the sensation of shear stress, rubbing, or a force that, if the wall were to be free to move to the right, would propel the wall to the right. So movement, momentum, is being transmitted. In other words, the flow is setting the wall in motion. Or you can think of it the other way around, as in the second problem there. The wall starts to move, and it's transmitting that motion to the stationary fluid. And that's been happening here. And so the question now, I have a volume of stationary fluid. It's two-dimensional. Why is everything two-dimensional?
It's easy.
Huh?
It's easier.
It's easier. Why is it easier?
Just two vectors, I guess.
What?
Just x, y vectors.
No, it's because your field of vision is two-dimensional. You know nothing. By the way, you know 3 dimensions because you have 2 eyes. That's the trick with the 2 eyes being in front of your head that enable you to see perspective, to compare 2 images that are slightly different. And of course, through the evolution of the brain, that comparison speaks of far versus near. And when you see something that's small, something familiar that's small, such as a lion, you are not scared because that means the lion is far. But when you see something really huge that's up in your face, like your cat when she wakes you up at night, then you're scared, okay? So that's the way we human beings get around the fact that we see 2-dimensional images. The one-eyed person sees a 2-dimensional image without perspective. Get it? But the brain is an amazing thing because it gets around to all sorts of things, including with this algebra thing that I brought up. All right. So a 2-dimensional body of fluid of one dimension h and another one L. The amount of fluid is fixed. I call it volume A. To teach you another lesson, because A goes with area. Why did I call it volume? Because it has 0 cubic centimeters in it. The area is a volume of zero thickness. Yeah. You can play jokes on people by switching these words, and if they contradict you, you say, wait, I meant to say a volume of 0 thickness, okay? It is fixed. And it is being set in motion by a plate of length L that enters here at time t equals 0. See, the bottom wall is being invaded by a solid plate entering from the left. Oh, what's outside this rectangle doesn't mean anything in this exercise. What happens beginning with the tip of the plate? Well, you've seen boundary layer theory. The tip develops a blunt boundary layer. The farther the plate proceeds, let's say it gets as far as that point, the boundary layer is thicker and longer. And yes, the fluid in this assumed system begins to move. But of course, not all of it moves. Only the fluid that's near the plate moves. And then, of course, this story ends at time t equals L over u. This is the speed u constant. At that stage, the boundary layer is as thick as it will ever be. And at that stage, the fluid in the assumed system is mostly stagnant. Get it? All right. Before we continue, we recognize this particular scale, which is the scale of boundary layer region generation or production or acceleration. Beyond this time, the fluid, the boundary layer fluid, which is moving to the right, is rubbing the stationary fluid and doing to it what I erased in this portion of the blackboard, meaning there's a diffusion of movement vertically with to the distance h. During a different time scale called t sub h, meaning this is like a two-stroke engine. First, you accelerate the fluid along the bottom wall during this time. Next, you transmit that movement vertically. Not you, nature here. Sorry, I didn't mean to say that you are not nature. We can bring that up if you want. During a different time scale, namely nu t sub h to power 1/2. In other words, the second time scale is t sub h, h squared over nu. All right? This is what's happening. The setting of this system of yours in motion happens during a time cycle interval of this scale plus that scale. So the time of accelerating that or transmitting momentum to this fluid is L over u plus h squared over nu, in which, of course, let me repeat, the product HL is fixed. And now comes the unusual idea. What would it take for my problem statement, one modification, for this time to be the shortest that it can be? By asking about the so-called minimum time in this particular drawing is to ask, in what configuration is momentum transmitted the fastest from the mover to the stationary. It's about making the transfer of something, in this case momentum, easier. You see? That's the question, which is not in the textbook of fluid mechanics. First of all, am I entitled to have a hunch about this? Might there be a minimum? Let's look. First of all, this h squared is the same as a squared over L squared. And if I sketch the behavior of this minimum time, so this is minimum time, versus, for example, L, it's easy to see that the first term, which I'll call Roman 1, increases as a straight line, whereas the second one is it's called a hyperbola, Roman 2. And the two terms add up to suggest in your mind a bucket-shaped curve, meaning with a minimum. The minimum has no place to be except at the L. You can think of it as not optimum, but selectable, which means optimal, at the intersection of the asymptotes. And here you encounter a method that's used a lot in the textbook called the intersection of asymptotes, which is a self-standing idea. Much more general than this example. It is the idea that if you want to find the answer to a kind of a complicated problem, don't waste your time on the complicated problem. Imagine the problem in one extreme, call it left, and then in the other extreme, called right. Each extreme so simple that you don't even have to write the problem and the solution down. And then you intersect the asymptotes. You've been taught this without being alerted many times in education, not just engineering, but in general. I'll mention one example in thermodynamics. At the undergraduate level, at the back of the book, you have steam tables. And the steam tables put there the properties of liquid, and then the rest of the properties of steam or vapor. The two extremes are there if you ask yourself. The extreme, let's call it on the right of the table or on the TS diagram, is the steam that's hot enough and low pressure enough that it behaves like an ideal gas. So one extreme is the ideal gas. The other extreme is the liquid itself, which is essentially incompressible, meaning that the extreme here is that of highly compressible, ideal gas, and over here, incompressible. Well, get to know the properties of your thing with that temperature, pressure, whatever they told you, in the two extremes. You don't exactly add and divide by 2, but you get a feel for where the dome will be, the dome. Not only the near saturated steam, but also the mixture of steam and liquid water. That is if you're in a hurry and if you know what you're doing. And only after that You can get curious about the textbook and the page at the very end where you have all this information. And with what I just, with the preview that I gave you, the intersection of asymptotes, you know on which page to put your finger to get to the exact estimate that concerns you. So the minimum time of momentum transfer is a scale that can be estimated because it's at the intersection of asymptotes, either as the first term evaluated at this particular dimension. In other words, this is term Roman 1, L over U. And by the way, before I could get to that, let me show you what happens when you intersect the two asymptotes. When you say 1 and then 2, and use this expression to calculate either L or H, you get these results. The dimension H turns out to be A nu over U to power 1/3. The other dimension L is A to 2/3, and then U over nu to 1/3. You can check these things yourselves by manipulating what's on the blackboard. And you can take, so that's basically what you get. But you can rewrite these things even better. If in either of these you substitute, instead of A, you put HL. In other words, you have an expression between H and L here, and another expression between H and L here. Combine these two things by eliminating A, and you discover that the vertical dimension must be the same as L times Reynolds number based on L to minus 1/2. This is the formula for the boundary layer thickness without making the assumption of slenderness. You see? And then if you make the mistake of buying your own material, this is Adrian, then you call this not boundary layer theory, but boundary layer according to the Constructal Law, because to sniff the presence of an opportunity to shape the system so that the system receives momentum the fastest. This is the attitude of nature called the Constructal Law of design occurrence in nature. But to see whether I claim too much, you're invited to take my course next spring called ME 438 and 555 for the graduate students, called the Constructal Law and Design in Nature. So, or Design in Nature for short. The useful item to retain is that first there was hydromechanics in the 1800s, or others call it hydraulics. Then came boundary layer theory, which gave birth to fluid dynamics of today, aerodynamics coming from Prandtl's laboratory. But what is classical and useful is asking to be questioned, you see, or to be regarded as one page in a book of history, a history that, of course, continues from day to day.